In this example we will create and examine PQ capability diagrams for a wind farm. Activate the study case 4.1, PQ diagram at 20 kV. Let us look at the network graphic. Here you can see the wind farm, which consists of 6 turbines. Double-click on a turbine to examine its parameters. You can see that this turbine has an active power rating of 2.5 megawatts. Here you can see the capability curve of the wind turbine. The red lines indicate the reactive power capability at different levels of active power output. All the turbines in the wind farm have the same active power rating and the same capability curve applied. Let us look at the capability curve in more detail. This dialog indicates that for each wind turbine, a number of capability curves have actually been defined. The capability curve which is applied depends on the voltage local to the turbine, so the values are entered in a matrix. The columns refer to the different active power outputs and each row of data refers to a different voltage value. The overexcitation parts of the characteristics are defined in the upper matrix, and the underexcitation parts in the lower matrix. The matrix configuration can be specified on the configuration page. Notice the shape of the characteristic in the top right-hand corner at higher voltage levels. Note that at the point of common coupling, the nominal voltage is 20 kV. The voltage set point in the external grid is 1 per unit. Having looked at the PQ capability diagram for an individual wind turbine, we will now create a PQ capability diagram for the whole wind farm, referencing the point of common coupling. To do this, we will use a DPL script. On the page called 04.1 Start Calculation of PQ Diagram, the DPL script can be accessed by clicking on the button. First, have a look at the description page. Here you will find a description of what the script does, depending on the values of the input parameters. Return to the Basic Options page. Here you can see the input parameters of the script. Note that the reference active power is 15 megawatts. This is the sum of the rated active powers of all the turbines. The number of steps is set to 100. The script will carry out the load flow calculation in each step, increasing the active power values from 0 up to 15 megawatts over the 100 steps. This is done once for the overexcited and once for the underexcited area. In the lower panel, you can find the external objects linked to the script object. Here, the reference PQ curve of the VTE standard, 4110, for 1 per unit voltage at the point of common coupling, is selected. Execute the script. Two characteristics are plotted. The blue characteristic represents the required reactive power capability according to the VTE standard 4110. The red characteristic represents the reactive power capability of the wind farm. You can see that the calculated reactive power capability of the wind farm at the point of common coupling meets the requirements of the standard, since the red curve fully encompasses the blue curve. Now, activate the study case 4.5, PQ diagram at 18.0 kV. In this study case, the voltage set point is changed to 0.9 per unit, i.e. 18 kilovolts. Due to the low voltage, the power from the wind generators is transferred by a higher current. Therefore, the loading of lines and transformers is higher. The maximum allowed loading can be set in this script parameter. In order to prevent equipment being overloaded, this parameter is set to 1, so that the reactive power of the wind turbines is automatically curtailed. Now run the script. A summary is printed in the output window, which shows that the maximum loading of the transformers is around 100%. Activate the study case 4.2, PQ diagram at 21.5 kV. In this example, the voltage set point is increased to 1.075 per unit, i.e. 21.5 kV. Run the script once more. In this diagram, the red curve indicates the reactive power capability of the wind farm at 21.5 kV, at the point of common coupling. Notice in the top right-hand corner of the plot, that the requirement is not being met. Reactive power compensation can be used to resolve this problem. In the wind farm network, you can find a capacitor bank. Double-click on the capacitor and have a look at its parameters. The shunt controller has a rated reactive power of 0.25 MW per step, and a maximum number of 10 steps. This results in a maximum rated reactive power of 2.5 MW. Now, open the script dialog and enable the automatic shunt control. This will set the actual step number of the capacitor bank to a maximum in the overexcited operating area, whereas in the underexcited area, the actual step number is set to 0. In addition, notice that the capacitor bank is already selected as an external object for the script. Run the script again. You can see that with the reactive power compensation included, at high power levels the reactive power requirement is met.